Hi boys and girls, this is lecture 4.9 in Unit 4, the last of our Unit 4 lectures. The topic, differentials. Newton's method is an example of the use of a tangent line to a graph to approximate the graph. In this case, we were using the tangent line to approximate zeros of the function. There are other situations in which the graph of a function can be approximated by a straight line. Notice the curve that is graphed here and then the tangent line at the point 0, 1. For a certain interval around that target point, you can see how closely the values on the tangent line approximate the values on the curve. This is useful information for approximating values on a curve, and there will be situations where we want to use a linear approximation at a point on the curve in order to approximate those function values. Consider a function f that is differentiable at c, then the equation for the tangent line at the point c f of c is given by, and notice this is just in point slope form, y minus f of c, the y value, is equal to f prime of c, the slope at the point c, times x minus c, then of course that is x minus the x value of the given point. We can rearrange this into y equals form simply by adding f of c over. Y equals f of c plus f prime of c times the quantity x minus c. This equation is called the tangent line approximation or linear approximation of f at c. In other words, we would use this to approximate values of our function near c by looking at the linear approximation values. Find the tangent line approximation of f of x equals 1 plus sine x at the point 0, 1. Notice that I've graphed the curve 1 plus sine x here, and I've also graphed the tangent line at the point 0, 1. We're going to find the equation of this tangent line, then use a table to compare the y values of the linear function, the tangent line, with those of f of x, the original curve, on an open interval containing x equals 0. Notice in the table I have already given y values at certain x values around our target point 0, 1. Once we create the equation of the tangent line, we will find y values at those points and compare to see how close the approximation is. So here is the equation of our tangent line approximation. We're going to need f of c, the y value, f prime of c, which is the slope at the x value that we've targeted, and then we're going to need to know what c is, the x value. So let's identify those things. We have our point 0, 1. So that means, of course, that c, the x value that we're interested in here, is 0. Therefore, f of c is going to be 1. We, of course, also need the slope at 0, so let's find the first derivative. F prime of x is equal to, since 1 is a constant, the derivative of 1 is 0, and then the derivative of sine is cosine x. F prime of 0 then will be cosine of 0, which is 1. So these are the three numbers that we need to plug into our tangent line approximation. Y equals the y value, 1, plus the slope at our particular x value 0, which was 1, times x minus our x value, which was 0. In rewriting this, I end up with this tangent line, 1 plus x. Y equals 1 plus x. So that's the equation of this line. Now let's look at the y values using this tangent line approximation to see how closely they compare to the actual function values. Of course, at the target point, they are exactly the same. But then as we move to either side of the target point, you can start to compare the function values with the tangent line values. They're still very close, and they remain close for a certain interval on either side of the target point. Obviously, as you go further and further from that target point, the values will begin to diverge. But for a specific region around the target point, the tangent line values are very close to the actual function values. Now let's talk about differentials. When the tangent line to the graph of f at the point c f of c, here's the equation of that tangent line, is used as an approximation of the graph of x, the quantity x minus c is called the change in x and is denoted by delta x. We've seen this before. When delta x is small, the change in y, denoted by delta y, can be approximated as shown. Delta y is equal to f of c plus delta x minus f of c, which is approximately equal to the slope f prime of c times delta x. For such an approximation, the quantity delta x is traditionally denoted by dx and is called the differential of x. The expression f prime of x dx is denoted by dy and is called the differential of y. So that leads to a definition of differentials. Let y equals f of x represent a function that is differentiable on an open interval containing x. The differential of x, denoted by dx, is any non-zero real number. Remember, that's just a change in the original x value. The differential of y, denoted by dy, is dy is equal to f prime of x dx. Let's compare delta y, the actual change in function value, and dy, the differential. Let y equal x squared. Find dy, the differential, when x equals 1 and dx equals 0.01. Compare this value with delta y for x equals 1 and delta x equals 0.01. This 0.01 is just representing a distance away from our initial value 1. Notice on the graph here I have drawn the curve y equals x squared, and I've also drawn the tangent line at the point 1, 1. Delta x, or dx, is 0.01, the distance away from our target value 1, which takes us to an x value of 1.01. Now notice that I've also put function values on the curve and the tangent line at 1.01. Now let's determine the difference between what delta y is and dy is. Delta y is the actual function value change from 1, 1 to this ordered pair 1.01, whatever this function value is. It's just the difference in function values on this particular curve, delta y. Dy, the differential, is the difference in the original point 1, 1 and the function value on the tangent line that we've drawn at the point 1, 1. Notice that is slightly different than the actual function value, but that is the differential. What we're going to find is that dy, the differential, is a very close approximation of delta y, the actual change in function value. First, let's calculate delta y. Delta y is simply the change in y value between the two data points. We'll find that by calculating f of x plus delta x, the function value at the second x, minus f of x, the function value at the first x. For this problem, that will be f of 1 plus 0.01. Remember, 1 was our initial target point, and then 0.01 was the distance away that was chosen, delta x, minus f of 1, which just means we need the function value at 1.01, and we need the function value at 1, and we need to subtract those two things. So delta y in this case, since our function is x squared, will be 1.01 quantity squared minus 1 quantity squared. This turns out to be 0.0201. So the change in function value from 1 to this new point is 0.0201. That means the new coordinates will be 1.01 and of course 1.0201. Since the original y value was 1 and the change is 0.0201, then the new y value is 1.0201. Now let's calculate the differential. dx can be found by taking the first derivative at our target value, f prime of x, multiplying that by the differential, which in this case is 0.01. We're going to need the first derivative for this, so let's find it. If f of x is equal to x squared, then f prime of x will be 2x. So for this differential, we're going to need f prime of 1 times the differential, which was 0.01. This is going to be f prime of 1. When you put that into the first derivative, you get 2 times 0.01, which means the differential is 0.02. Look how closely this approximates the actual change in function values delta y. And of course, this means the coordinates of the point on the tangent line here are 1.01, 1.02. So using differentials to approximate a change in function values is another way that we use tangent lines to approximate values on a curve. Let's see how each of the differentiation rules that you studied in Unit 2 can be written in differential form. We'll start with y equals x squared. The derivative dy dx is equal to 2x, and written in differential form, this means dy is equal to 2x dx. Letter B, we would have dy dx is equal to 2 cosine x. But writing that in differential form means I would have dy is equal to 2 cosine x dx. I might want to put this in parentheses just for clarity's sake. Here we have dy dx is going to involve the product rule is equal to first times the derivative of the second, which is negative sine x, plus the second times the derivative of the first. Simplifying this a little bit would give us negative x sine x plus cosine x. But now let's write this in differential form. dy is equal to negative x sine x plus cosine x, and then of course dx. And in letter D, dy dx will be, if I rewrite this as x to the negative 1, I will have negative x to the negative 2, which can be written as negative 1 over x squared. Now let's write this in differential form. dy is equal to negative 1 over x squared dx. Let's find differentials of a couple of composite functions, starting with y equals f of x equals sine 3x. So dy dx is going to be cosine 3x times the derivative of 3x, which is 3. This can be rewritten as 3 cosine 3x. How do I write this as a differential? dy equals 3 cosine 3x dx. Now for our second example, we're going to need to use the chain rule. We have dy dx is equal to 1/2 x squared plus 1 to the negative 1/2 times the derivative of what's inside, which is 2x. In simplifying this, notice that the 1/2 and the 2 cancel, giving me x over the square root of x squared plus 1. Now to write this as a differential, I would write dy is equal to x over the square root of x squared plus 1 dx. Differentials can be used to approximate function values. As we have seen, to do this for the function given by y equals f of x, use the formula f of x plus delta x is approximately equal to f of x plus dy the differential, which is equal to f of x plus f prime of x dx. Yet let's use this formula to try to find an approximate value for the square root of 16.5. We're going to pretend as if we don't have a calculator and no other method for finding this value except for using differentials. Notice I have the graph y equals the square root of x here, and I've also graphed the tangent line at the point 16, 4. Now the function value at 16.5 is also plotted here, and you can see that at that point the value on the tangent line is very close to the actual value on the curve. In fact, we don't see a distinct separation between the tangent line and the function value. So you can see that when we find the differential, which will actually be the function value at 16.5 on the tangent line, it's going to be a really, really close approximation to the actual function value on the curve. So let's see how this works. We can see that the function, of course, is f of x equals the square root of x. In this case, we're going to take 16.5 and separate this into 16 plus 0.5, where x is our target value and 0.5 is our differential, delta x or dx. And so we're really going to be looking for f of x plus delta x, which of course is f of 16.5. Now to do so, let's take f of x plus f prime of x times dx, the differential. Now I will need the first derivative here, so let's find the first derivative of the square root of x. First, I'll rewrite this as x to the 1/2 power so that I can use the power rule. F prime of x then will be 1/2 x to the negative 1/2, which is 1/2 square root of x. We're going to need to know the first derivative at x equals 16, which will be 1/2 square root of 16, which is 1/8. We also need to know the function value at 16, which hopefully we do know. F of 16 is the square root of 16, which is 4. And of course, our differential we already decided was 0.5. So here are the three numbers we'll need: 1/8, 4, and 0.5. Let's use our formula to find an approximation for f of x plus delta x, which is f of 16.5. I'll change colors for dramatic effect. Therefore, f of 16.5 can be found by f of 16 plus f prime of 16 times the differential dx, which actually is 0.5. I should have probably inserted that in there. So this is going to be f of 16, which is 4, plus f prime of 16, which is 1/8, and the differential 0.5. This ends up being 4 plus 1/8 times 1/2 is 1/16. And this is approximately equal to 4.0625. There's our approximate value. Differentials to the rescue. We didn't even have a calculator. Way to go, boys and girls. That's it for today's lecture, and that concludes the Unit 4 lectures. Someday, many years from now, when you are attempting to compliment the one you love, this might work. Or not. God bless you, boys and girls.